All right, here we're going to be looking at differentiability and different ways that the derivative can fail to exist. We've looked at a lot of different ways that it can actually exist, but we're going to look now where it doesn't exist, because it's easier to figure out where something can or cannot occur rather than looked everywhere where it can. All right, so anyway, we're going to focus in on that, and we're going to look at local linearity, a couple examples of when it fails to exist. And then that'll be what's on this video. Anyway, so if we look at these different ways that it can fail to exist. Number one, it can fail to exist at what's called a corner. So with a corner, a common function for a corner. Okay, so if this is our graph, a common function for a corner is an absolute value. So right here we have y, a sketch of y is equal to the absolute value of x, and right here's your corner. Right there, that's your corner. So it cannot exist at a corner, and that's because if we look right up here, a function will not have a derivative at a point if the slopes of the secant lines fail to approach a limit as x approaches a. Okay, so if you look at the slopes of the secant line, they don't approach any limit. Think about what the slopes of this line are coming in together. You know, like the slope of this line is -1. So the slope of this line here is -1. Here's -1. Here's -1. Here's -1. So as you approach 0, these slopes are -1. But here, as you approach 0, these slopes are +1. We know it doesn't have a derivative because these slopes are not approaching the same value. Okay? So these slopes are approaching -1 and these slopes are approaching +1. Since they're not the same value, there is no derivative at that point. There's a limit, but there is no derivative. On the second one, we're looking at what's called a cusp. And a cusp is similar, looks similar to a corner, but especially on some graphs can have a half cusp, half corner. Man, that is gorgeous. Look at that drawing. Anyway, it is like, for example, this is a y is equal to x to the 2/3. Doesn't really look at it, but it is. And again, right here is your corner, and then these slopes are getting more and more negative, but these slopes are getting more and more positive as they're approaching x equals 0. They're not approaching the same value, so there is no derivative at that point. All right, the next one is going to be a vertical tangent. Vertical tangent is like a cubed root, so y is equal to the cubed root of x. All right, so if we look at that, okay, so this is going to be tricky for me to draw on this thing, but it's going to look something like that, where right here at x equals 0, all right, right there you have your vertical tangent. That means your slope is straight up and down. It's undefined. Okay, so there's no slope there. So how can you have a derivative if the slope doesn't exist? Because, hey, derivative is the slope. Makes sense. So we have a corner, cusp, vertical tangent, and then the last one is a discontinuity, which we've been talking about for a while, but never looked at it from the lens of a derivative. But a discontinuity would be like a piecewise function. So you have, you know, this part going that way, and then you have this part going that way. Doesn't really matter. But for these piecewise functions, you notice the slope here. First of all, the graphs don't even meet up. So if there's any kind of discontinuity, then there is no slope. But there can be piecewise functions that have derivatives at a point. And what you have to do is you have to check, well, do the limits equal each other, and then do the derivatives equal each other. So those are two things that you have to look for. Okay? So looking here, differentiability implies local linearity. So a good way to think of local linearity is to take a point on a certain graph, and to zoom in on that point over and over and over again to see what happens. So right here we have a graph, okay, and if we take this graph and we zoom in on a specific point, let's see if this works. So we're going to take this point where my cursor is, and we're going to zoom in on that point. Whoops, yeah. And I want you to notice, because eventually if we zoom in a lot, now look at that line, okay, yeah, it kind of bends there, but if we zoom in a lot on a particular point, what do you notice about this line? Well, you can still kind of, if you look closely, there's still a little bend in it, but if I zoom in, zoom in, zoom in, zoom in, zoom in, eventually this line becomes a straight line. That is local linearity. If you take a single point on a graph and zoom in as close as you possibly can, that line eventually will become straight. However, if we take a point, for example, let's make this the absolute value. Here we have the absolute value, and I'm going to take this point right here, right at the corner, and I'm going to zoom in, zoom in, zoom in, zoom in. Alright, if I zoom in on this point right there, I'm trying to get in the center. Okay, if I keep zooming in, will this line ever, 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 ever become straight? No. Since it does not hold that property of local linearity, it cannot be differentiated at that point, meaning it does not have a derivative. That's what local linearity is. So in order to have a derivative, it has to be locally linear at that point. Okay? Let's take a look at this example here. It says the function fails to be differentiable at x equals 0. Tell whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. So on your own, go ahead and try this and tell me which one of those this looks like. Look at some of the examples and try it, pause it, and then come back. If you graphed it, you'll know what it is, but if you didn't, hopefully you didn't, because you'll be able to tell what it is, hopefully, right away because of this part. But this is going to be a vertical tangent. Going to be a vertical tangent. All right. Do that without graph. You need to be able to do that without graph and tell what it is. And let's go ahead and do another example. So find this example. So look for this example in your notes. Find all values of x where the function h of x is equal to blah. The cubed root of 3x minus 6 quantity that, and then plus 5 is differentiable. Okay, so the first thing that we want to do is figure out where it's differentiable, where it's not. So you got to think about, well, on this one, it looks like it might be a vertical tangent. And the key thing is, no matter what it is where it's not going to be differentiable is what makes this thing under here not possible. Okay? So what you want to do is you could graph it, that's fine, but go ahead and try this on your own and see what happens. Okay, try this on your own. You might be looking for a vertical tangent. I don't know. You look on your own. Guess at it first. I want you to guess at it first and then try it. Then come back to the video and look at it. So what you should have come up with is that this is for, that's all reals. Whoops, all reals. Except at I got x equals -2. Okay, because you cannot put a negative in there. You can have negatives underneath here, okay, because it's a cubed root. If it's square, that's something different. It just wouldn't exist. Where it doesn't exist, it's not differentiable. But here, yes, you can have 0 under here because -2 is what makes this 0. Okay, -2 is what makes that 0. And that's where you would have your occurrence of a vertical tangent in this case. All right. Another way to write it, remember, in interval notation would be, you would have from -infinity to -2, not inclusive of -2, so that's unioned with -2 to infinity. Okay, so either of those is fine, but this is interval notation here. Okay, so I think that's all that I have for this set of notes, and the next set of notes will be on another video to finish those up.